So let us talk about differential equations. A brief review. We've already seen them in detail in our mathematics course in the first semester. Let us briefly review them and see how they're going to be useful. So what you're going to see again and again in this course on network analysis are ordinary differential equations. And a special case of ordinary differential equations, generally ordinary differential equations which are linear and which have constant coefficients. Now what does ordinary differential equation mean? Differential equations can be nonlinear, they can be time variant, they can have different forms. So that is more a subject of some advanced study. But in this course we're talking about circuits which are linear, which are generally time invariant. So the governing equations are also linear, and they are also their coefficients are constant. So we'll talk about these things in a little more detail. So what is the general form? What is the general form of an ordinary differential equation? This is something that you have seen. Let us write it again. So an ordinary differential equation with constant coefficients can be written in general as an x nt, where xn represents the nth differential, this represents the nth differential of x, right? Plus an minus 1 xn minus 1 t plus so on. It will continue up to the first differential, and then the constant term a0 multiplied by xt equal to ft. So this is the general form of an ordinary differential equation which is linear. So this is an ODE which is linear and which has constant coefficients, because the coefficients a0 to an are constant. These are constants. So it's an ordinary differential equation because there is only one independent variable, which is time. So we have derivatives with respect to time only. In partial differential equations, in contrast to this, we have differentials with respect to other quantities. So it can have differentials with respect to time and space. So time, x, y, and z, 4 independent variables. Like for example, in electromagnetics, you study partial differential equations. So that's why this is an ordinary differential equation, because there is only one independent variable, that is time. It's a linear differential equation because it obeys linearity. Now what is linearity? Linearity is the property wherein the differential equation obeys the property of superposition and homogeneity. Superposition and scaling. So and scaling. So what does this mean? A system is linear if a differential equation is linear if the response to an excitation f1t plus f2t is the response is x1t plus x2t, wherein x1t is the response to f1t alone and x2t is the response to f2t alone. And when you take both of them together, both of these forcing functions together, like this is a forcing function here, so the response to f1t plus f2t is going to be the sum of x1t plus x2t. Similarly, scaling, so if the excitation is multiplied by alpha f, some constant alpha, so you have alpha f1t, the response or the solution also gets multiplied by alpha. So if the response to f1t was x1t, the response to alpha times f1t is alpha times x1t. So that is the definition of a linear differential equation. The property of superposition and the property of scaling is satisfied. So in this general case that we have written down here, ft is called the excitation. This is the excitation function. If ft is identically 0, that means it is 0 for all times t, right? Then the right hand side of this equation becomes 0 and the differential equation is also homogeneous. So it's a homogeneous differential equation, homogeneous ordinary differential equation, which is linear and which has constant coefficients. Linearity can, in other words, be also defined as in terms of the presence of only the first degree of the derivatives or their higher orders, in the sense that you'll have in the differential equation you'll have xt and its derivatives, but their degree is going to be 1. Only first degree xt and its derivatives will be present. Like for example, you'll have nothing like xt squared or xt the first derivative squared, or even the product of xt or the first derivative, for example. These terms will not be there if the differential equation is linear. Then the highest degree derivative within the differential equation, which in this case is n, is called the order of the differential equation. So this is how we write an ordinary differential equation, and we know that it's a linear ordinary differential equation, so it obeys the principle of superposition. So that means that if the forcing function or the excitation function is a combination of some forcing function f1t multiplied by a constant a and another forcing function f2t multiplied by a constant b, then the response is also going to be a combination of x1t and x2t, where x1t and x2t are respectively the responses because of f1t and f2t. So the principle of superposition is satisfied, and that's because this thing is linear. Now, how do we solve homogeneous differential equations? Quickly, we'll see. So you have a homogeneous differential equation and you want to solve it. You want to write down the solution for it. It's very simple. We assume a solution, and that solution has a general form, and it is applicable to almost all ordinary differential equations with constant coefficients and which are linear. So you have an ordinary differential equation which is given by this general law. It's an ordinary differential equation which is linear, which has constant coefficients, and which is homogeneous, in the sense that the forcing function is identically 0. Ft is identically 0. So you assume a form of the solution. You assume that xt is some constant c multiplied by e to the power pt, right? So if you assume that this is a solution to this equation, you can substitute the solution in the equation, and you see that when you differentiate this once, you'll get a p outside, this will stay in. If you differentiate it twice, you'll get a p square outside, this xt will stay in. So if you substitute this whole thing inside the left hand side, you'll get something like this. An, the nth derivative of this is going to be p to the power n, right? And again you'll have c e to the power pt plus a n minus 1. Then again the n minus 1th differential is going to be this. This will continue till you get a0. Then you can take this c e to the power pt outside, and inside you will get what is called the characteristic equation of the differential equation, which is an equation in powers of n, unknown in various powers of n. So this can be written as sum where hp is a polynomial in P. Now this whole thing can be 0 at P is equal to minus infinity, no doubt about it, but that's a trivial solution. The non-trivial solution will be only when HP is 0. So the solution to the homogeneous differential equation is xt is equal to c e to the power pt, where p is given by the characteristic equation hp is equal to 0. That's how you solve an ordinary differential equation which is homogeneous. Like for example, in case you have a simple differential equation given by x t, first differential, minus 2xt. You can also write this as a single dash is equal to 0. The characteristic equation for this would be p square, p minus 2 is equal to 0. You have to substitute for each differential degree of x, you have to substitute the corresponding power in p. So this is p, this is first derivative, so p to the power 1. This is the 0th derivative, there is no derivative term here, so p to the power 0, which is this 1. So p minus 2 is 0, that means p is equal to 2. That means the solution to this is xt is equal to c e to the power 2t, and you can verify this by putting it in here. When you put c e to the power 2t, substitute it, you will see that what does it give you? It gives, now differentiate this once, you get twice c e to the power 2t, and then minus twice c e to the power 2t is equal to 0. So 0 is equal to 0. So this is a solution to the differential equation. So if you have multiple roots, then the differential equation is going to be, by the principle of superposition, the sum of the various terms present. Like, for example, if you're able to factorize HP, so let me summarize. The solution to the homogeneous differential equation with constant coefficients, written in the general form like this. Is given by, the solution is given by c e to the power pt, where p is given by the solution of the characteristic equation. HP is equal to 0. So if you're able to factorize HP, you're able to say that HP, which is basically a polynomial in P, is given by an P minus Pn, sorry, a P minus P0 into P minus P1, P minus Pn minus 1. It's a polynomial of nth order. If you're able to write something like this, then HP is equal to 0 for P is equal to P0, P1, P2 up to Pn minus 1. That means HP is 0 for any of these, and xt is equal to c e to the power P0t is one solution, and xt is equal to c e to the power P1t is another solution to this homogeneous differential equation. And by the principle of superposition, the sum of all of them is going to be a solution, because for 0 excitation, for 0 ft, this is the solution, and for 0 ft, this is a solution. So when you sum the two, 0 in the first case and 0 in the second case, then the solution is going to be the sum of these two. So in general terms, if you're able to factorize HP into distinct factors like this, the solution is going to be CE xt is equal to CE P0t plus, this is of course going to be C0 plus C1, this is 0, this is 1, because they're going to be different constants, plus C1 e to the power P1t plus so on and so forth, Cn minus 1 e to the power Pn minus 1t. So please remember that this is a solution to the differential equation given by this, whose characteristic equation can be written like this. And it is a solution because of the principle of superposition, because independently C0 e to the power P0t is a solution, and independently C1 e to the power P1t is a solution to this, and the sum also has to be a solution because the right hand side is a 0. So when you substitute this in the left hand side, you'll get a 0, and when you substitute the two of them, you just add the 2, it's going to be a 0, because when you substitute this alone, it has to be a 0, and when you substitute all of them, it has to be a 0 on the left hand side. So then there are distinct cases which arise because of different kinds of characteristic polynomials that you'll get. So for example, if you have a repeated root, your case becomes slightly different. If you have a complex root, your case becomes slightly different. So there's a small table that I'll draw, and you must have already seen it, which will tell you about the nature of the roots, and correspondingly will tell you the form of the solution. So what are the roots of your characteristic polynomial, and what is the form of the solution? So we have already seen that if your roots are multiple distinct real roots, right, p0, p1 up to pn minus 1, then the solution is c0 e to the power p0t plus c1 e to the power p1t plus cn minus 1 e to the power pn minus 1t. If you have a single root p0, the solution is just going to be e to the power p0t. This is a single root. If you have multiple roots, but they have multiplicity, but they are same in the sense that they have a multiplicity k. That means p is equal to, the roots are p1, right, k times. Like for example, in case of the polynomial p minus p1 to the power k is equal to 0. What are the roots of the equation? The roots of the equation, there are k roots, and all of them are equal to p1. There are k roots, and all of them are equal to p1. So in case that is the case wherein we say that the roots are p is equal to p1 with multiplicity k, we can write down in this case the solution to be c0 e to the power p1t plus c1 t times e to the power p1t plus c2 t square times e to the power p1t plus, if we continue up to c to the power k minus 1 e to the power t to the power k minus 1 e to the power p1t. This is going to be the form of the solution. Like for example, in case you have p is equal to p1 and p1, that is, the original equation was something like p minus p1 whole square is equal to 0. So you have two roots at p1. The solution xt would have the form c0 e to the power p1t plus c1 t times e to the power p1t. So the solution is going to have two terms, and the degree of t in the solution is going to be k minus 1. So here k is 2, so the degree is k minus 1, that is 1. In case you have complex roots, sigma plus j omega is equal to sigma plus minus j omega. Complex roots will always occur in complex conjugate pairs because the coefficients a0, a1 up to an minus 1 are real. So the complex root, if it occurs, it will be sigma plus j omega, and it will be sigma minus j omega. In that case, the solution can be written as simply as m or c, or if you want to write m1, you can write m1 e to the power sigma t cos omega t plus m2 e to the power sigma t sin omega t. or you can also write is given by x double dash t minus 8 x dash t plus 16 xt is equal to 0. We first of all write down this is an ordinary differential equation with constant coefficients. We write down the characteristic equation. The characteristic equation can be written down by inspection. This is degree 2 differential, so p square minus this is a degree 1 differential. 8 will be written down straight away plus 16 is equal to 0. This can be factorized. This is p minus 4 whole square is equal to 0. So there are two roots and both of them are real and both of them are at 4. So you can write down the solution by writing the general form c1 e to the power 4t plus c2 t e to the power 4t. So this is the solution, and for writing the values of c1 and c2 you need initial conditions. We'll talk about this in more detail in subsequent lectures, but the general solution is going to be something like this, and you will get a clearer solution or a more specific solution if you know the initial conditions, and then you're able to find c1 and c2. Similarly, another example you can write down, like for example, if you have the differential equation given by a differential equation which is given by x double dash t plus 2x dash t plus 5xt is equal to 0. So we write down the characteristic equation p square plus 2p plus 5 is equal to 0, and the roots are going to be, this is the characteristic equation hp, the roots are going to be p. If you factorize this, you'll get minus 1 minus 2j and minus 1 plus 2j. So you can write down the solution xt to be m1 e to the power sigma is minus 1, so minus sigma t. Then you have cos is going to be 2, right? So cos 2 2t plus m2 e to the power again minus t sine 2t, because this is sigma plus minus j omega. So omega is 2 and sigma is minus 1. This is one way of writing it. The other way of writing it is just as m sine omega t, which is 2t plus 5 into e to the power sigma t. This is the other way of writing it. Again, you can find out m1, m2 or m and phi by the initial conditions.